All right, we're going to be talking about rational functions, and this is kind of a long lesson, so it might be one where you have to skip around and see where you need help. But a rational function has the form of f of x equals p of x over q of x. Okay, where if we think of p of x and q of x are polynomials. Okay, so you could have like x squared plus 2 over 4x squared minus 3x minus 4, or you could have 1 over x. Okay, so just some vocab there. An inverse variation function is a rational function in the form of f of x equals a over x. Okay, and what we're going to be dealing with when we're dealing with the inverse variation, at least today to kind of reference, is the parent function. The parent function of an inverse variation is f of x equals 1 over x. So in other words, we're going to say a is 1. Okay, we call that graph of that parent function a hyperbola. Most likely you're not going to be tested on that, but that is the name of the graph there. Okay, so that vocab is going to help us here. So we're going to go ahead and graph that inverse variation parent function. Okay, the f of x equals 1 over x. And I have this table that I like to use to show work in the middle. So we're going to have 1 over x there. That's our rule. The first thing we need to do is figure out what a vertical asymptote is. And that's a vertical line. Vertical lines run, if you think of it, the x-axis, your vertical lines, or your asymptotes, run through the x-axis. Okay, you run down through them, so it's x equals something. All right, and so really what we're trying to identify in this is when we're looking at our function, especially in a fraction form, you can't have a denominator ever equal 0, or you can't divide by 0. So when you set the denominator equal to 0 and solve for x, that's your vertical asymptote. So in this case, x can't equal 0. If x is 0, you get 1 over 0, and that's undefined. And so I'm going to put that asymptote right here. Okay, 1 over x, which we're going to call 0. 1 over 0, that's undefined. Okay, and so on a graph, we show that by using a dashed line. So here is my vertical asymptote. Okay, it's at the equation x equals 0 because it goes through the x-axis at 0. So the characteristic of this graph, the vertical asymptote, is x equals 0. Now a horizontal asymptote, okay, the line that we approach but will never, or we'll get really, really close to, we may end up crossing it, but it runs horizontally, will be seen when we actually graph this. Okay, so using this as my starting point, I'm just going to say, well, I'm going to make x 1, 2, 3, negative 1, negative 2, and negative 3. And you can use other numbers, but I'm going to use those for now. So 1 over x, 1 over x, 1 over x. Okay, so notice I'm just putting parentheses where x would go. And I'll plug those values in, or substitute those values in. So 3, obviously 1/3. 2, that's 1/2. So let's actually write it as a decimal rounded to the nearest tenth there. So 1/3 would be 0.3 if we rounded it to the tenth. 1 over 1 is 1. 1 over negative 1 is negative 1. 1 over negative 2, negative 0.5. And 1 over negative 3, negative 0.3. Okay, so we have negative 3, negative 0.3. We have negative 2, negative 1/2. We have negative 1, negative 1. We have 0 is undefined. We now have 1, 1, which skips over to here. We have 2, 0.5. And we have 3 and 0.3. Okay? And so we have this picture of developing here. You see this line. It would be really nice if we knew what 10 was. So if I just put 10 down here, that's pretty easy. 1 over 10 is just 1/10 or 0.1. It's getting like really, really close to the x-axis. Okay, so let's try to actually hit the points here. So I have this line, this curve that's getting really close to the x-axis. And I know over here it's going to get really close to the y-axis because I have an asymptote there. Okay, now I could actually plug in 1/2, right? 1 over 1/2, or how many halves go into 1? That's 2. So it jump up to there. And how many thirds go into 1? Well, that would be 3. So it would be like right there. And then you'd have 4, and you could try 10. You'd be at, okay, you're getting really close there. And the same thing here. We could put -10 in for x. So if I were to substitute in -10, that'd be 1 over -10, which would be -0.1. So that would be like really, really close. So I have this curve that does this. It's really close to the x-axis. And then if we were to substitute -10 in, or -1/10 in, we get -10 on y. Okay, so we have that. Hey, that is the parent function. Notice it doesn't exist right along the x-axis. We graph, and then we jump and we hit way up here and start graphing again. Okay, the horizontal asymptote is, in this case, the x-axis, which is y equals 0. That's the horizontal line we're getting close to. The domain, well, the domain is all real numbers except for one real number. That one real number is x cannot equal 0. So all real numbers except x equals 0, and the range is actually all real numbers as well, except y equals 0. Right? It exists for everything except for those where those asymptotes are. Okay. Very good. So let's go ahead and look at how we can use that parent function and compare it to some others. So let's graph g of x equals -1 over x, and we're going to compare it to 1 over x. So I put -1 over x there. Okay, so all these are going to be -1 over something. Pencil it there. All right. So the thing that x cannot be is 0 again. So that happens to be my vertical asymptote. Okay, x equals 0. That's when my denominator equals 0. So I have this asymptote that does this, goes down the y-axis, and x equals 0. Try to stay as close as I can to the y-axis, but there we go. And if I were to plug in values, let's say 1, 2, and 3, so I get 1, I get 2 there, and 3 there. Notice now it's just -0.3, -0.5, and -1. If I substitute in -1, -2, and -3, well, now I have a positive 1, a positive 0.5, or positive 1/2, and a, it's supposed to be negative, but a positive 0.3. And so really what's happened is my graph is reflected here. So that 1, 1 that was here is now all of a sudden down here. Okay, that 2, 1/2 is now at 2, -1/2. Okay, and so on. So the graph has flipped over that x-axis. Now some would say, well, what didn't it just reflect? Couldn't have reflected this way, and it could have. Okay, but since the negative's up on top, we're going to say it's going over the x-axis, and I'll kind of elaborate on that here in a minute. But plotting our other points. Sorry about that. Oops. All right, so notice if I just do a quick switch back and forth, It's just reflected over the x-axis. Okay? And so that's our comparison, is a vertical reflection over the x-axis. Now, like I said, some of you go, well, why couldn't it have gone over the y-axis? And it could have, but when the negative is not attached to x, so if the negative was down here, I would say it was going over the x-axis. Now the reality, or excuse me, the y-axis. Now the reality is it doesn't really matter. The negative floats around, but since it's up here with the 1, I'm going to say it's over the x-axis. It's a vertical reflection. Okay, horizontal asymptote this time is still at y equals 0. The domain is still all real numbers except x equaling 0. And the range is still also all real numbers except y equals 0. All right. Well, let's look at another one. Notice now a is changed from 1 to 3, from -1 to 3. Okay, so we've got 1 to 3, and let's see how that changes it. So we now have 3 over x here. I know it becomes really tedious setting up your table, but definitely helpful here. So vertical asymptote, what would make the denominator equal 0? Well, what value of x? It would have to be 0 still, so x equals 0. So we're still holding at that is our undefined. So our vertical asymptote. It eventually will change, but hasn't yet. You want to start thinking ahead, maybe what would make that change, right? What would make it not be 0? Okay. Let's go ahead and put our 1 in, 3, 1. 3 over 1 is 3, so I get 1, 3. So every time it was, well, actually, let's finish this. 3 over 2 is 3 halves, which is 1.5. 3 over 3 is 1. 3 over -1, -3. 3 over -2. 3 over -2 is -1.5. And 3 over -3 is -1. Okay, and so finishing this off, 1, 3, 2, 1.5, and 3, 1, and -1, -3, -2, -1.5, and -3, 1. And so our graph, again, is going to, you can see the curve really well here. It's going to get really close to the y-axis, or the x-axis and the y-axis. If you're like, well, how do you know it's going to get really close to the x? You know that's your asymptote. Well, once again, I could plug in 10. 3 over 10 is 0.3. Oops. I were to say this is 10. Right, that's 0.3. So that's going to be like right there. I could do the same thing for -10. 3 over -10 is -0.3. And that's going to be like, what? It's actually further down than I have it. So what's happened? Well, you think about it, this point was in our previous graphs. So let's go to our parent function. From our asymptotes, where our asymptotes cross, we went over when an up one is at 1, 1. Well, now, from where our asymptotes cross, right here, right, there's our horizontal at y equals 0. Well, we're going over 1, and rather than up 1, we're up 3. Okay, our parent function, 1 over x, was that. It was at a half, and then at a third. Well, notice 1 times 3 is 3. 1/2 times 3 is 1.5, and 1/3 times 3 is 1. So this graph has stretched this way by a factor of 3. And the same thing's happening over here, but it's just stretched downward. Okay, we were at -1, and it's went down. Okay, and we were at 1/2, and now we're at -1.5. And we were at -1/3, and we're now at -1. So this is a vertical stretch by a factor of BAFO, 3. Okay, our graph is stretching away from the x-axis. And what's doing that? Well, this value of 3 here. So if this was 5, it would be a vertical stretch of 5. If it's 7, that would be a vertical stretch of 7. So A controls our stretch and shrink. Okay? So we think of A, we think of our stretching and shrinking there of the parent function. Okay, so it's a vertical stretch and shrink. Okay. So domain, still all real numbers except x cannot equal 0, so at x equals 0. And range is still all real numbers except y equals 0. All right, let's take a look at another one. So notice now I have negative 2 over x. So if you think of what we just talked about, well, here's our a term. The 2, how is that going to change it? Well, that's going to be that was a vertical stretch of 3, so a 2 will be a vertical stretch by a factor of 2. The negative, remember when we had a negative back here, the negative was a vertical reflection over the x-axis. Okay, and what's the 3 do? Well, this is like a plus k, right? So if you think of it as f of x is equal to a over x, we'd have a minus h down there. I know we haven't got to that yet, but we have a plus k. And k is a vertical translation. So this is actually going to move our graph up 3. Let's see how that works here. So we have negative 2 over x plus 3. So negative 2 over plus 3, 2 over plus 3, negative 2 over and plus 3. Getting a little messy here. Negative 2 and plus 3 and negative 2 plus 3, negative 2 plus 3 and negative 2 and plus 3. Well, first thing we want to do is figure out what our vertical asymptote is. So what will make your fractional piece undefined? Well, what will make the denominator 0? It's still when x is 0. Okay. Now, even though we have a 0 here, like negative 2 over 0 is undefined, you can't add something to something that's undefined, so this whole thing is undefined. That is our vertical asymptote, so it's going right here. Okay. Horizontal asymptote, we'll see here in a minute. Let's see. Okay, we're going to put 1 in. Negative 2 over 1 is negative 2, plus 3 is 1. Going to put 2 in. Negative 2 over 2 is negative 1. Negative 1 plus 3 is 2. We put 3 in. Negative 2 over 3 is negative 2/3. Plus 3 is 2.666, or 2 2/3, or 2 1/3, excuse me. Sorry, 2.3333, or 2.3, if we round it there. Okay? So we have 1, 2, and 2 1/3, or 2.3 if we round it off to the nearest 10. And we put in negative 1. Okay, we get 5. Put in negative 2. And we get 4. And we put in negative 3. And we get 3. Oops. Boy, don't mean to do that. Sorry. 3 and 2/3, or 3.7 if we round it. Okay, and so plotting our points, 1, 1, 2, 2. Okay, and 3 and 2 1/3. All right, and then plotting our points for the next one, -1, 5. Oh boy, my pen's giving me a hard time here. Okay. And -2, 4, I think I've got it working good there. And -3 and 3.7. All right. Okay. And so you'll notice you're like, what in the world? Did I graph this wrong? Well, no, think about it. I mean, this translation up 3, it means what was our vertical asymptote at y = 0 has moved up 3 units. It's now up here at y = 3. And so when we put that in, you start looking at it, it makes a little more sense. You see this curve, and we start approaching there. Okay, and we get infinitely close over here. Same thing goes on this side. Okay, close, we're approaching, and there. So if you were to put in, it's again like 10, -2 over 10 is -2/10, plus 3, well, that's 2 8/10, or 2.8, which is like right there. Okay. Horizontal asymptote has moved up 3, so it's now at y = 3. Domain, all real numbers except, well, domain is x, so x can't equal 0, so all real except x = 0. Range is now all real numbers except y = it's no longer 0, it's 3. All right, I think we have one more graph. And notice on this one, the movement is on the bottom. So we have a 4 on the bottom. Well, this is a horizontal translation. And we're adding 4, so it moves to the left. It's kind of backwards. And then remember the 2 is a vertical stretch. Bafo 2. Okay? So looking at this, we have 2 over x plus 4. I really don't like writing my fractions like I am here, but it's the only way I can really fit it. You want to make sure you know that the whole x plus 4 is on in the denominator there. So remember that. So now you got to ask yourself again, what is going to make that denominator equal 0? Because that is your vertical asymptote. So here, what's going to make that 0? Well, x plus 4 = 0 when x = -4. So now, my vertical asymptote is at -4. Right? When I put -4 in, -4 plus 4 is 0. 2 over 0 is undefined. So we move our graph, our asymptote, from going down the middle to down -4. We actually can kind of see it. Use that dashed line there. X = -4. That is our vertical asymptote. Notice it's not moving up and down, so technically our horizontal asymptote is still going to be y = 0. We're going to see that. So it's like we've moved our origin. I mean, you kind of think of it like that. It's not really what happened, but you're kind of moving those crosshairs there. Let's go ahead and put some numbers in. So let's put -3. Okay. So 2 over -3 plus 4. Well, or excuse me, -3 plus 4 is 1. 2 over 1 is 2. Okay, and we put -2 in there. -2 plus 4 is 2. And we get 2 over 2, which is 1. So keep in mind this whole thing's in the denominator. Boy, it might be better to put some parentheses around those so you remember that. I've almost made that mistake going through it here. Okay, and we put -1 in. -1 plus 4, 2 over is 3, and so we get 2/3, or round to the nearest tenth, 0.7. Okay, and so we go -3, 2, Okay, negative 2, 1, and negative 1, 0.7, right? And by the way, if we would have put 10 and kind of continue that out, we'd have 10 plus 4 or 14, 2 over 14, which is really close to 0 there. I think it's like 0.114 or something like that. Okay, so really close. So this line does something like that, and it's going to zip up here. Okay, and we could be more accurate if we put in more points, but hey, and go ahead and put in negative 5. And we have that negative 5 plus 4, and we get negative 2 in there. Put in that negative 6, do the math there. You end up with negative 1 and negative 7, and we end up with negative 2/3 or negative 0.7. Okay, and so negative 0.7 is there. We get negative 1 and negative 2. Okay, we know that we're going to be approaching there and there. All right, so domain, all real, except now it's moved to the left, so except x equals 4. And the range, all real, except y equals 0. Okay, so hopefully you're starting to see this. Okay, all right. Well, like if you were, that would be day 1 of a lesson. Okay, day 2 would start right here. In day 2, we really start talking about asymptotes and discontinuities. So identifying discontinuities, which are vertical asymptotes, and I'm introducing the word holes there. Okay, a discontinuity is a vertical asymptote or hole, and I'll explain what each of those are. A function is discontinuous, in other words, it doesn't continue. You have undefined areas if it has a vertical asymptote, or a movable discontinuity, also known as a hole. Functions are undefined at their asymptotes and or at their removable discontinuities, which we call a hole. And a function is discontinuous if a real value of x will cause your denominator to have a value of 0. So just like we've done in all these other problems, if the denominator equals 0, we have a discontinuity. If the denominator can equal 0, we have a discontinuity. Okay? That will happen anytime you have an x down there and you get you set it equal to 0 and you get a real number. So for instance, what values of x will cause these equations to be undefined, or in other words, discontinuous? Well, let's look at this. This first equation. I want to know what will make the denominator equal 0. Well, let's try it. X squared plus 4. What will make that 0? Well, we subtract 4 from both sides. We take the square root. All right. Well, now notice the square root of a negative. That's this is actually going to give us an imaginary number. Oops. Plus minus 2i. Okay. There are not any real numbers that will make this discontinuous, and we're not dealing with imaginaries here. Okay. We're only dealing with the real number line. So this graph is actually continuous. Okay. So if you try to set the denominator equals 0 and you get an imaginary number, then the graph's continuous. In other words, there aren't any holes and there aren't any asymptotes. If you were to graph it, you would never have to pick up your pencil. You'd have a smooth curve that you can keep graphing forever. Okay? It's continuous because you have an imaginary solution that would make the denominator 0. Okay? So let's look at this next one. What will make it discontinuous? Well, There are two ways I'm going to approach it. First, I'm going to do exactly what I did here. Say, okay, what makes 2x squared minus 18 equal 0? Well, I'm going to add 18, so I get 2x squared equals 18. Divide by 2, x squared equals 9. And take the root, impose the root, you got to put plus minus square root of 9 is 3. So positive and negative 3, those are my discontinuities. What values of x? Right here. We've solved it. Okay, what I want to know, also, I'm going to add to this, what are those discontinuities? Are those discontinuities holes, or are they asymptotes? I know we haven't talked about holes, and this book doesn't go into holes much, but the one way you can find that out is really pretty easy. What we're going to do is we're going to factor this denominator. We're going to say, okay, what comes out of 2x squared and 18? Well, that's 2. Okay, and I'm left with x squared minus 9. And then this difference of 2 squares, so we'll keep factoring. That's x plus 3, x minus 3. Okay, and so we've now taken care of the bottom. Well, on the top, let's see. Can we factor it? Well, two things that multiply to make 4 and add to 4. Yeah, that would be x plus 2 times x plus 2. Okay, now, if you can cancel out, so you're multiplying everything on top and bottom, okay? You're not adding or subtracting anymore, so between your quantities. So if you can cancel out a whole set, like if this is x plus 2 and this is x plus 2 and we can cancel, that's a removable discontinuity, which is a whole. If you can't, then both the things on the bottom that would make our denominator function equals 0. Those are my asymptotes. And by the way, those are the same things we had here, right? But for now on, I'm going to be factoring. I have an asymptote at x equals 3 and x equals negative 3. Okay. So let's try in a different fashion here. So let's look at this first one, or this one right here. Y equals 3 over x plus 1 quantity squared. Well, it's already been factored on the bottom. What will make this 0? Well, x plus 1 equals 0 when x equals negative 1. Can I cancel out an x plus 1 on top and bottom? Nope. So this is my discontinuity, and it is an asymptote. This next one, I'm looking at it. The denominator's already factored for me. Can I cancel anything out of the numerator and denominator? Well, notice I have an x and an x. I can cancel out an x. Okay? If I would have said, what makes this 0? Well, x could be 0, and x minus 6 can be 0. So, what makes my denominator 0? Well, let's go before we cancel it. 0 would, because that would be 0 times something, which would give me 0, or 6 would, because 6 minus 6 is 0, and 0 times 6 would be 0. Okay, so these are the two things that make it 0. Well, since I canceled out that one, this thing right here is a whole. It is a removable discontinuity. I have canceled it out. Because I canceled it, it's a whole. In fact, if you were to graph this, and you look at when x equals 0 on your graph, you would see a little skip in your graph. Okay? And this one right here, this is an asymptote. Okay? So, graphically speaking, like I'm going to just do a quick sketch here. I kind of have an idea of somewhat of what it would look like, but okay, so let's see. We would have this. We'd be trucking along, and then at x equals 0, it would skip over. And then we'd have an asymptote right there at x equals 6. Okay, and then your graph would pick up and do this over here. Okay, so notice right here, there's a hole. Okay, that's when x equals 0. All right. Let's take a look at this next one. So I'm going to go ahead and factor this. This is x plus 3, x minus 3. And now notice on top I have an x plus 3. Okay, what makes the denominator 0? Well, x equaling negative 3 would make a 0, and x equaling positive 3 would make a 0. Okay, well, these two cancel, so this is a whole, because I canceled it out. This is an asymptote, because I didn't cancel it out. All right, and one more here. Let's go ahead. We'll factor the top. Difference of two squares. So x plus 1, x minus 1. I hope you're good at factoring. And down here we have x plus 1 and x minus 3. Okay, what makes this 0? Well, x equaling negative 1, and makes this 0, x equaling 3. Can anything cancel? And yes, this cancels this, so that makes this a whole, because I removed it, and this is an asymptote. All right. So that deals with vertical asymptotes and wholes. Okay? The thing that we haven't talked about are horizontal asymptotes. And that's actually a lot easier. It's very wordy here, but I'm going to read through it and then I'm going to show you how to do it. We'll make it a lot simpler. Okay? So the horizontal asymptote tells approximately where the graph will go when x is really, really big or really, really small. It is possible that your graph will cross a horizontal asymptote. Now, in a vertical asymptote or a whole, it's not possible to cross it. But in a horizontal, it is. It could actually be running really, really close to it and bounce over and then just run right beside it. Okay? To find the horizontal or slant asymptote, and notice I added a term now, slant, and I'll show you what that is. Compare the degrees of the numerator and denominator. And here are the rules. If the degrees of the numerator and denominator are the same, then the horizontal asymptote is at you divide the leading coefficients, and that gives you your horizontal asymptote. If the denominator's degrees are greater by any margin, then the asymptote is going to be at y equals 0. And if the numerator's degree is greater by a margin of 1, then you have an oblique or a slant asymptote, which we have to use polynomial long division to find. So let's take a look at that, how that looks here. Okay, so we have this graph, we have all these equations, and I put those rules, these rules right here, on this next page, kind of in a box here. Okay, find the horizontal or slant asymptote for each. So what we're going to do, if the degrees are the same, so what I'm going to look at is, here I'm looking at my degree. This is a first degree because it's a power 1. This is a first degree. I'm ignoring the 5 and the negative 1 for a minute. Okay, first degree and first degree. They're the same. So really, since they're the same, I just look at their leading coefficients. Well, the coefficient is the number in front, so 2, and there's a 1 in front of this one. 2 divided by 1 is 2. So my asymptote is at y equals 2. Okay, that's my horizontal asymptote. Now you might be saying, well, what in the world? How do you know that? Well, remember, the rule is the horizontal asymptote tells us where the graph will go when x is really, really big or really, really small. So let's focus on the really big for a minute. If x is really big, say like 1,000,000, okay, that would mean I'd have 2 times 1,000,000. Oops, put my 0 on a little, okay, 1,000,000. So 2 1,000,000s, and then I have 1,000,000. 1,000,000. Okay, so that means 2 times 1,000,000, which is 2,000,000, and 1,000,000. Well, 2 times 1,000,000, 2,000,000 divided by 1,000,000 is 2. You might ask, well, what about the 5? Well, really, when you have 2,000,000, 5 is not much. Right? If you have $2,000,000, you're like, oh, they $5, you know, I'll buy something for $5, no problem. Okay. And you have $1,000,000. That one, well, here, you know, you spend $1, no problem. Okay, or you get 5 more bucks up here. I guess it would be more like it would be no problem. Okay, so 2,000,000 divided by 1,000,000 is 2. you have this extra little piece. We're not going to worry about that. By the way, those extra little pieces are why it could actually jump over the asymptote. Okay, it could actually cross over. But that's why that happens. You have when it's really big, it's like having 2 divided by 1. It's 2. The extra little piece doesn't matter. That's why we ignore it. Okay? So, that was the rule that we used here. Let's take a look at this. Notice my degree, first degree, second degree. Okay, the numerator or the denominator's degree is greater. Okay, well, that would be like having, if we use our million example again, we have 1 million, right? 1 million divided by, and we'll ignore the 2 because that's minor compared to a million, divided by 1 million squared. Well, what is 1 million squared? Just so you know, that is 1 trillion. A million divided by a trillion, dude, yeah, a million divided by a trillion. I mean, that's like something really big going into something kind of small, right? I mean, how many trillions fit in a million? Well, there's a million in a trillion. Okay, so this would be like 1/1,000,000th, which is really, really close to 0. So this is small over big. By the way, just a side note, when we say there's like $1 trillion and people just throw around the word trillion now, next time they do that, think about what it means. It means a million. So when you say like 20 trillion, that's 20 million, man. Okay. Anyway, my asymptote is, since the degree is bigger down here, y equals 0. Comparing my degrees, the same degree, I have 2 over 1, so y equals 2 over 1, which is 2. Okay, this next one, degrees are the same. Okay, so I compare it, 1 over 3 is y equals 1/3. And remember, these things don't matter. Even though there's an x here, that'd be like 3 trillion, right? Minus 2 million. Not that big of a deal. Okay? So we just ignore that. It's 1/3. Okay? Notice degrees are the same. We just take 4 and divide it by 3. So y equals 4/3. Okay? We ignore these things. Degrees are the same. Okay? So we have 5 over 1. So y equals 5. But notice you have a 3 at the end. So this would be like having a million divided by a million, right? Or 5 million divided by 1 million. Well, that's 5 plus 3 extra. So we have to add on that 3 that's on the outside here. We can ignore these things because they're part of the fraction, but the 3 is a whole number. Got to add that on. So my asymptote's actually at y equals 8. Okay? And this last one, notice the last one. Degree is bigger on top. Well, if the numerator's degree is greater by a margin of 1, it's an oblique or slanted asymptote. Okay, so it says use polynomial long division. Let me show you how all this works here. All right. So I'm going to take x minus 2 and divide x squared plus 3x by plus 2 by it. Okay, so x times what is x squared? Well, that's x. X times x is x squared. X times negative 2 is negative 2x. Okay, we subtract, which means we add the opposites. We're subtracting this whole thing, right? So that means this becomes negative and this becomes positive. Flip our signs there. So we get 0, and we have 5x, and plus 2. Bring down that 2. X times what is 5x? Well, that is 5. 5 times what, or 5 times negative, or 5 times x is 5x. 5 times negative 2 is negative 10. We subtract, which means we add the opposites. We flip the sign, so we get 12. So we have a remainder of 12, so we go plus 12 over x minus 2. Now, when we did polynomial long division earlier this year and we put it in this format, it just seemed kind of like, oh, whoop-de-doo. Well, notice this up here now. If I rewrite this in terms of y, I'm going to say y equals, And I'm going to put the 12 over x minus 2 first. And then I'm going to say plus x plus 5. Now remember, I mentioned vertex, or excuse me, I mentioned my my transformation form here earlier, right? Well, that form is what I'm going to use when I'm talking about this. So y equals a times x minus h, which I have right here. Here's a, here's h, plus k. Well, k is usually your horizontal asymptote. But k in this case is this whole thing. That's a slant asymptote. And you know what x plus 5 is. You've dealt with equations before. If I were to actually, let me kind of draw a line here. If I were to actually graph this, x plus 5, we go up, it's a linear equation. 1, 2, 3, 4, 5. Okay, we have this line that has a slope of 1. It does something like this. I know that I have a vertical asymptote at 2, right? That's what makes this 0. So at 2, okay, and so I'd have to end up dealing with right here. I'd have like here where I asked them to, I'd probably have another branch. Okay, and I know it's like this and not here and here because my slope, or my a, is positive, so my slope is going up from left to right. So my graph has to be increasing as x is going up. Y has to be going up. Okay, those are all things we'll see. But for now, I don't think we're going to be dealing with tons of slant asymptotes. But there we've got it. Okay. Now that we know about horizontal asymptotes and vertical asymptotes, we can graph some more difficult ones. And really, just so you know, we only have 2 graphs left. Okay, and we are almost done. I realize, like I said, it's a long lesson. It's a 2-day lesson in class. Okay, so graphing in this format. Notice I now have a numerator that has a bunch of stuff on it and a denominator that I'm graphing. First thing to do is figure out the vertical asymptote. That should be easy. What makes this 0? Well, that's when x equals 4. So we start here at 4. Okay, now you could have your 2 times x plus 3 and your x minus 4. Okay, so you'd have 2 times 4 minus 3 and 4 minus 4. Now really that's 0, so we just get undefined. Okay, so you have at 4, you have this asymptote. Okay. Now if I put 3 in, I get 2 times 3, which is 6, or 6 plus 3, right, which is 9. Okay, and then I have 3 minus 4, which is, excuse me, I put the 3 on the wrong side. That's ridiculous. Unbelievable. What a rookie mistake. Okay, well, let's go ahead and calculate. That's 9. And then I'd have 3 minus 4, which would be negative 1, so I'd have negative 9. So at 3, I'm at negative 9. There we go. Okay, and then let's go ahead and keep going with that. There we have put 2 in. 2 times 2 is 4. 4 plus 3 is 7. And then we have 7 over 2 minus 4, which is negative 2. Okay, so that's negative 3.5. Okay, and so we're now at 2, negative 3.5. And we'll keep going. We'll get 1, and we have 2 times 1 is 1, or 2 plus 3 is 5. And we have 1 minus 4 is negative 3, which is approximately negative 2.7 if we round it. Okay, and so we get 1 and negative 2.7 right there. All right. Now, we should be able to figure out our horizontal asymptote without having to finish the graph. So I'm going to look for my horizontal asymptote now, just like we did over here. Okay, well, look at our degrees. This degree is 1. This degree is 1. They're the same, so we divide our coefficients. Well, 2 divided by 1 is 2, so our horizontal asymptote is at y equals 2. So I'm going to go ahead and I'm going to put that in here. Y equals 2. Okay? So you'll notice in my graph, I don't have a lot of points here that are way up here. Right? All these points are negative. So let's say if I were to put in like negative 10, just really quick. 2 times negative 10, that's negative 20. Plus 3 is negative 17. Right? And then negative 10 minus 4, well, that's negative 14. Well, negative 17 divided by negative 14, well, negative divided by negative is positive, and 17 divided by 14 is like 1.2-ish. So now, right here. So my graph's doing this, and like that, and then like zips over here. Now, we could be more accurate in here if we were to calculate more points, but that's fine for what we're doing. Okay, so if I go ahead and plug in the rest here, let's go ahead and put in 5, 6, and 7. Now, this is taking quite some time, but when we calculate it out, this would be 13 over 1, which is 13. Okay, this would be 15 actually over 2, which is 7.5, and 14, let's see, 17 over 3, which is 5.7-ish. Okay, so again, 5 is 13, it's way off the graph. 6 is 7.5, so we're like right there. 7 is 5.7, which is right there. And in fact, if we were to put in, oops, let's get that 5.7 in there again. Okay, if we were to put in 10, that would actually be 23 over 6, which is like 3. It's almost 4. Okay, it's let's see, 3. So 3, 8, this curve down like all that is right. Except there's another way to graph, or excuse me, y equaling 2. It's right there. There's another way to graph this, and that's how we're going to graph this last one. Okay, we're actually going to rewrite it in this format first. All right, and the thing it does, well, it helps us to figure out some asymptotes, but it also just makes dealing with it I think, a lot easier. All right, you can see the reflections and stretches and stuff. But just really quick, looking at it, I have my asymptote. Right, the degree is the same. It's 1 and 1, so horizontal asymptote is y equals 4. Okay, so we go to y is 4. Vertical asymptote, well, what makes the denominator 0? Well, that's negative 2, x equaling negative 2. Okay, so we go here. Okay, I'm going to rewrite it in this format, and really what does that mean? It means you're doing polynomial long division. You're saying x plus 2. How many x plus 2's go into 4x plus 3? You may be going like, what, I got to do that again? Well, it's actually really fast. X times what is 4x? Well, that's 4. That's 4x and 8. Flip our signs and add here. Get 0 and negative 5. Minus 5 over x plus 2. Right? So we've changed it already. So this really changes to f of x equals negative 5 over x plus 2 all plus 4. Which tells us, right, here, this is your k, that's your horizontal asymptote. This is your vertical asymptote. And remember, this is your vertical stretch, shrink. Okay, and so this is going to, or a reflection in this case. Okay, so my graph's going to go down from left to right, so it's going to start up here, go down here. All right, I know that No matter which one you use, you can either use that, or this one to graph it. It doesn't matter. I know my domain is going to be all real except x equaling -2. And my range all real except y equaling 4. Okay? So I'm going to go ahead and use my -5. Actually, you know what? Yeah, let's use our -5 over x plus 2 plus 4. Okay? I know at -2 is here. That's going to be undefined. Okay, I'm going to put in my -1, 0, and 1. Okay, -1 inputting it. I'm not going to fill in the middle, but inputting that gives me -1 out. 0 gives me 1.5, and 1 gives me a 2.3. Okay, there's my undefined. Then I have my -3, my -4, and my -5. -3 gives me 9. -4 gives me 6.5, and -5 gives me 5.7. Okay, obviously I've dealt with these already, but we can go through and we plot them. We get -5, 5.7. Okay, -4, 6.5. -3, 9. So you can kind of see your curve developing. You calculate 10, but it's getting close to that line. And then -1, -1, or 1, -1. Oh, excuse me, -1, -1. And then 0, 1.5. And then 1, 2.3. And once again, doing something like that. And we describe it. This is the -5. Well, the negative is a vertical. You know what, actually, we should always start with our horizontal translation. So we've got the 2, the +2, is a horizontal translation. Left 2. You notice we went to the left 2. The negative is a vertical reflection over the x-axis. Bafo 5. And then the last one is the +4. And let's list that up here. +4, or we'll list it over here, is a vertical translation up 4. We always start with our horizontal translation. We end with our vertical translation. Okay? Always. That's a key piece there. All right. Well, that's plenty. That's all I got for you there. Good lucky.